Let's do some chain rule problems with exponentials, starting with the derivative with respect to x of e to the cosine x. So cosine x is inside the exponential function. The derivative of e to the x is just e to the x. So the derivative of e to the cosine x is going to be e to the cosine x. We're going to leave the inside function alone, but then we have to multiply by the derivative of that inside function. So we have times the derivative of cosine x is negative sine x. So we'll leave our answer as negative sine x times e to the cosine x. And the way I think about these problems is I just think when the exponential function is involved, I'm basically just going to copy the exact same function and then remember to multiply by what's up in the exponent there. So we have negative sine x, e to the cosine x. Now let's find the derivative with respect to x of 3e to the x squared. Well, this 3 is a constant multiple, so I can just go ahead and let that hang out there. The derivative of e to the x squared. So here I have that function e as the outside function, and so I always can just go ahead and think about it as kind of copying it down, e to the x squared. That's technically the derivative of the outside while leaving the inside alone. And then we just need to multiply by the derivative of the inside, which is 2x. The derivative of x squared is 2x. We have times 2x, leaving us with the final answer of 6x e to the x squared. So just make sure that we do have that e in the base raised to the x, and then 2 is the exponent of the x. Here, let's find the derivative with respect to x of 4 to the cotangent x. This one's a little different because it's a general exponential. I have a base of 4. Let's go ahead and remember the derivative with respect to x of b to the x is going to be natural log of the base times b to the x. We're going to use both this and the chain rule to find the derivative here. So it's going to look like natural log of the base, which is 4, times 4 to the cotangent x. So instead of x, we have cotangent x. So we leave the inside alone, and then times the derivative of that inside. And the derivative of cotangent x is negative cosecant squared x. So I'm going to go ahead and leave my final answer as negative cosecant squared x times natural log of 4 times 4 to the cotangent x. Here, let's find the derivative with respect to x of 2 over 3 to the x. What you might be thinking is that you don't really see a chain rule, and you're right. The way that it's currently written does not require the chain rule. You might be thinking, let's move forward with a quotient rule. I see a quotient. And that's true, but typically I don't want to do a quotient rule unless I have to, and especially when either the numerator or denominator is a constant. I don't even have a function of x over a function of x. So what I'm going to do is I'm going to rewrite this so that I don't have to use the quotient rule, but what's going to happen is I'm going to have to use the chain rule. When I rewrite this as the derivative with respect to x of 2 times 3 to the negative x. When I bring 3 to the x to the numerator, it's going to make that exponent negative. And now this is a chain rule because I don't just have x here, I have negative x. Let's go ahead and move forward with the derivative, remembering that I cannot multiply the 2 and the 3 together. I have to follow order of operations. So that 2 is just a constant multiple that's going to hang out there. So I'm going to have 2. And then the derivative of 3 to the negative x. We're going to have the natural log of that base. So the natural log of 3. And then 3 to that inside function, negative x. And then times the derivative of negative x, which is just negative 1. So here's how I'm going to leave my answer. I'm going to multiply the negative 1, the 2, and the natural log 3, and I'm going to leave it as negative 2 natural log 3 in the numerator, and then I'm going to bring 3 to the negative x to the other side of a fraction bar and make it 3 to the positive x. So I'm going to go ahead and choose to leave my answer like this. Here we'll take the derivative with respect to x of e to the negative x minus 5 to the cosecant of 2x. Because they're subtracted, I can do each one separately, and each is going to require a chain rule. So here, e to the negative x, this one comes up quite often, and we want to be able to do it pretty quickly. So when we have e as the base, again, we can just go ahead and think about it as just kind of copying it. So e to the negative x, because the derivative of the exponential is itself, and just don't forget to multiply by the derivative of the inside, which in this case is a -1. So I'm just going to stick that negative on the outside. So the derivative of e to the negative x is negative e to the negative x. And then we'll go ahead and work on this one here. So we're going to go ahead and put minus. This has a base of 5. So let's start with natural log of the base, so natural log of 5. And then we'll have 5 to the cosecant of 2x. So what we've done so far is basically the derivative of the exponential while leaving the inside alone. And now I have to multiply by the derivative of cosecant of 2x. And that's actually its own chain rule. So what's going to need to go right here is the derivative of cosecant of 2x. All right, well, the derivative of cosecant is negative cosecant cotangent. But what we have to do is put negative cosecant of the inside, cotangent of the inside. So the derivative of cosecant, negative cosecant x cotangent x, but in place of x, I have 2x. So what we've done is the derivative of cosecant, while leaving the inside the same, times the derivative of 2x, which is 2. Okay, so now to write this final answer out, we have negative e to the negative x. Let's see, we have this negative times the subtraction that's here, so that's going to leave us with a positive. So I'm going to put plus, I'll put the 2 way over here, that's multiplied, so I'll put that in the front. So 2 natural log 5, and then 5, actually I'll put the exponential last, so I'll put cosecant of 2x cotangent of 2x times 5 to the cosecant of 2x. I mean, multiplication is commutative, so the order doesn't really matter, but typically we have constant multiples first, and then I'm choosing to leave the exponential piece last here. Let's now recap the chain rule with exponentials. If we have the derivative of just e to the x, that's e to the x. The derivative of e to a function of x, like g of x, is just e to the g of x, that exact same function, times the derivative of the inside, the part up in the exponent, so times g prime of x. If we have a general exponential with the base of b, that derivative is natural log of the base times b to the x. If there is a function of x up in the exponent of that general exponential, then it's natural log of the base, b to the g of x, times the derivative of the inside. So I don't want us to think about these as new rules. They are just applying the chain rule to the derivatives we already know for e to the x and a general exponential.